Hey guys, are you there?
Yeah.
I'm here.
Well, it's come to mind here that one traditional expertise that astronomers are supposed to have is the proper keeping of time.
The ability to tell time.
Yeah, so I need
And
to
to display the
apologize.
right
Yeah,
information
I
about it.
had to display the correct information about it. So apologies to everyone who was confused by seeing the 9 p.m. start time on our slide. We completely forgot that the slide actually had the time on it, and we will correct that for next week. So I hope there wasn't too much confusion. It didn't look like anybody dropped off in a frustrating huff. Um, how are you guys doing tonight?
Well, we're doing fine, except
Good.
that we made the decision to switch to 9:30 because it was getting darker later at night, which would have been a good decision. Except tonight it decided to be completely foggy, so it wouldn't matter whether we started at 9 or 9:30. So,
Yeah. Oh
well,
well.
Oh well.
That's the
welcome
way
to
it goes.
astronomy in the Bay Area.
Yeah. Yeah.
Yeah.
So for those of you who live here in the East Bay, it was raining most of the first half of the day, and then it was pretty moist the rest of the day. So it never really looked like we were going to have the opportunity. So it is a virtual viewing night. And we do have a number of items for you. But before we get started, I want to remind everyone that the Chabot Space and Science Center is still closed. We will be opening in the fall. Currently, the plan is to open the Science Center again to the public in November. We rely on your donations to keep us afloat in the meantime. And so if you are so inclined, please click on that donation button on your Facebook screen or visit the ChabotSpace.org website where you can make a donation from there. So thank you much. I also want to thank Fremont Bank, community supporter of the Chabot Space and Science Center, for their ongoing support of our programs. Gerald, we have some other announcements. What's coming up in a couple of weeks? We've got
I
a
think
lunar eclipse.
lunar eclipse. Yeah, yeah. So very early in the morning on May 22nd, or I'm sorry, May 26th, uh, we will have a total lunar eclipse. It will start at about 1:47 in the morning, and it that's when the moon starts to slip into the outer part of the Earth's shadow called the penumbra. That part of the shadow is not very bright, so you'll just notice a slight dimming of the moon at that point. But then about an hour later, it will start to slip into the darker umbra part of the shadow. The umbra is the dark part that's kind of has a reddish hue to it. And the moon will start slipping into that about 2:45 in the morning. And by about four, I believe it's 4:11 is when it reaches totality. And at that point, it will only remain in totality for about I think it's 13 minutes or something like that. It's not very long. Um, so anyway, it's a very early morning event for those of us here in the Bay Area. It'll start at 1:47 in the morning. The Chabot Space and Science Center is going to live stream the event, so we will come on the air at 1:30 in the morning. We will have at least two cameras on two different telescopes and maybe a third. So you'll get some different views of the eclipse as it's happening. You'll be able to watch it with us. We'll provide some commentary, maybe do some interviews, and definitely take questions and comments from the audience. So if you're up for staying up all night, we hope you can join us, and we'll watch the moon slide through the shadow of the Earth.
I have one really important question about that night. Which one of us is bringing the coffee pot?
The big coffee pot.
That very big coffee pot. Yeah, it's going to be a long night, but
Yeah.
it'll be fun. It's
Well,
also
to make matters worse, I will have just come back from my trip back east, so
oh, it's going to be worse for
I
you.
will be on
Wow.
East Coast time, so I will
That's the
be
wrong direction.
really
Yeah.
messed up.
Oh,
Yeah.
man.
We'll have a cot set up for you just in case.
It's a good idea. Alan is reminding everyone that it is Astronomy Day.
Yeah.
So
Yeah,
happy Astronomy Day. And, it figures it's cloudy, of course.
of course.
So Astronomy Day was started by a gentleman named Doug Berger right here in the Bay Area. And there was an association started around that whole concept and bringing together astronomy clubs and bringing together other amateur astronomers called the Astronomical Association of Northern California. And that's where Astronomy Day came from. It's a product of the Bay Area. So thank you, Doug, wherever you are. And Alan, thanks for the reminder about that. I had forgotten about it completely. So I guess where do you want to start?
Oh, I don't know.
Want to start with where we left off last week?
Well, you know what? Let's start with one thing here. For those few people who are watching who might actually be able to see clear skies, if you're far enough away from the Bay Area, there's something going on right now that you might want to check out. The moon and Mars are both very close to each other. I've got a little image here that I'll share with you. Right there. So this is what you will see in the night sky if you were to rush outside right now and look. And if you aren't in the Bay Area where it's covered with fog, but away from the Bay Area, you'll see the crescent moon in the low in the western sky, and right next to it you'll see a little orange dot, and that is the planet Mars. They are both right close together. If you use a pair of binoculars, you can easily get both of them in the field of view with a pair of binoculars. If you've got a small telescope that's got a wide enough field of view, it has to be about 1.5 degrees wide. But if you've got a small telescope that'll do that, even with a telescope, you can get both of them in the same field of view. So that's going on right now. Now, of course, they're really not close together.
Hopefully
Mars,
not.
yeah,
No,
Mars right now is about 200 million miles away, whereas the moon is only about 240,000 miles away. So it just happens to be that they're lined up so that they look
Right.
close to each other.
We seem to lack a good term for when things are close visually, but
Yeah.
not close in distance. So maybe visually adjacent.
Angularly close.
Optically adjacent.
Optically adjacent.
Yeah.
Okay,
Yeah,
that's
It's like an optical
Optically
binary, and with
Yeah.
stars, this is an optical conjunction.
Yeah, because if Mars was right next to the moon, it would be very, very large.
And not good for not good
Yeah,
for
not
the
good
Earth.
for us, not good
And
for
it would be,
anybody.
yeah, be really bad for those tides.
Yeah.
So I was going to continue where we left off last week.
Yeah.
And last week, we left everyone with this image of M5, the globular cluster. And while we were talking about M5, I was snapping 30-second shots and collected about a dozen of them. And of that dozen, I'd say 10 or so were worth keeping. And this is of course what one of our raw images look like when we're doing live imaging from the telescope. But I'm going to share a processed version of this that looks a lot better. There you go. And this is what happens when you get as much of the noise out of the image as you can and you stack the images together. And this was just a quick stack that I did this afternoon. And I think that came out pretty good considering what we had to work with.
There are a lot of stars in that.
There are a lot of stars there. Globular clusters, of course, are some of our favorite things to look at. They photograph really well. They're nice and bright, so they're a good target when we're doing our virtual astronomy programs. And they're also really interesting. They contain some of the oldest stars in the known universe. Every spiral galaxy that we've observed has them. at least those that are close enough where we could actually see the globular clusters. Andromeda certainly has a good collection of them. The Milky Way has about 150 of them. And there's been various theories over the past century on what their origins are and what their nature is. What we do know is that the stars in a globular cluster are close to 13 billion years old. They're very old stars, and we know that because they lack the heavier elements that are typical of newer stars that are, when I say newer, I'm talking about stars that are younger than 10 billion years, for instance. And these newer stars have a lot of the heavier elements that we're used to seeing here on Earth, like, having carbon and having iron and heavier elements and metals. But these older stars are really only showing the primordial elements that are believed to have been in place when the universe was very, very young. So that's how we know they're very old stars. We're able to look at the spectrum and look at the absorption lines and determine their composition. So we have about 150 of them, like I said, in the Milky Way galaxy. There was a period of time where people thought they were the cores of other galaxies that had collided with the Milky Way. And there's still a lot of people who think that might be the case, but the leading theory is that they formed together out of giant clouds of hydrogen gas and formed at roughly the same time and are gravitationally bound as a result of their proximity to one another. So there might be 100,000 stars or more in this one cluster, and they're all bound together into a region of space. They're going to maintain this proximity for their entire lifetime, and that's why they look like a giant ball of stars, because that's in fact what they are. Gerald, one of the things I notice on this cluster is that there seems to be two distinct families of stars, at least. We see a lot of blue stars. We see a lot of red stars, and you might want to talk about that because it's one of the interesting characteristics of M5.
Well, as Richard was saying, this is a very old object. All the stars in this object are more than 10 billion years old. When it first formed, it had a full spectrum of stars, high mass stars, medium mass stars, and low mass stars. High mass stars don't last very long, though. So a high mass star, say a star with 20 times the mass of our sun, would only last maybe 200 or 300 million years. Whereas a star with less mass than our sun could last 12 or 15 billion years. So the stars that we see, because this thing is so old, they're all lower mass stars, stars that are able to survive for 10 or 12 billion years. Some of the stars are reaching the end of their lives. They're already swelling up and becoming giant stars, or even possibly supergiant stars, red giants. So you see a lot of orangish colored stars. Those stars are likely stars that are starting to reach the end of their lives, and stars swell up when they reach the end of the lives. They cool off on their outer part of the star, and that gives them a kind of yellowish or orange color. Other stars are still white or slightly yellow. Those are the stars that are still on the main sequence. They're still fusing hydrogen. They're still cooking along as more or less normal stars. But then you see all those blue stars, and blue stars shouldn't be there. Blue stars, when we see stars that are blue, we associate that with hot stars. And hot stars, in order to be a hot star, you have to have a lot of mass. But as I said, all the high mass stars have already gone away. So why are we seeing blue stars in this cluster? And it turns out that the blue stars result from the fact that so many stars are so close together. The stars are orbiting around the galaxy or the cluster in highly elliptical orbits. So they go in close to the center and then they swing way out and then they go back in. When they're in close to the center, they're very close to each other. And you can just see that by looking at this image. When they get that close, they can sometimes bump into each other or pass so close to each other that one star, if it's a little more massive than the other, will actually pull gas off the other star. And so you can have one or two things happen. You can either strip away the outer envelope of the star, exposing the much hotter interior, which will appear as a blue star, or you can have two stars that actually collide with each other. They merge, and now you've had two low mass stars that merge and become one high mass star, and all of a sudden now you've got a very hot star again. So the term that astronomers use for these blue stars, we call them blue stragglers, because they are sort of stars that somehow have changed their nature and appear blue even though they are very old stars.
Great.
Hey, we have an
Okay.
interesting question from Margot. Bob Schluck tried to answer it, but I'm not sure he understood the question quite right. Margot says, how many moons would be visible in the Jupiter or Saturn night sky? And I assume she means from Jupiter or from Saturn, how many moons would be visible? And that would vary quite a bit,
Yeah, really.
depending on
Yeah.
where they are in their orbits.
Yeah.
Bob had said that Jupiter and Saturn are in the morning sky now, and that's from our perspective. But I think what she was asking is from the planet Jupiter or Saturn.
Well, it's probably easier. It's probably easier to answer the question for Jupiter, right? And Jupiter's got what 80 some odd moons, right?
Yeah.
And some ridiculous number that keeps going up. Saturn, it seems that some of the moons would be lost in the ring.
Yeah, actually quite a few of them. Yeah.
And so you'd be looking up. Well, I don't know where you'd be standing on Saturn.
you wouldn't be standing
Or
because you don't have a surface to stand on.
It is in the cloud platform. You'd be looking up and you'd be seeing the ring, and or the rings of Saturn, and the moons would be embedded in those rings. So
some of the moons,
or
not
some
all
of them anyway,
yeah,
not
yeah,
all of
yeah.
them. Yeah,
Those
but
rings would be very bright too.
Yeah.
Yeah, but the same thing is true for Jupiter. The perfect answer to her question is you would not see any moons because Jupiter doesn't have a solid surface. If you try to stand up, sink way down, and you wouldn't be seeing anything.
You'd be plummeting to your death.
Yeah. Yeah. But Jupiter has, depending on who you talk to, 79, or I think there's some talk about it, it's up to 83 or something like that.
Yeah,
but a lot of these moons are very, very small. They're maybe 1 or 2 kilometers in diameter. And unless you catch it when they're in sunlight and just at the right distance and angle, you might not be able to see them. Yeah. We have objects pass by the Earth that are actually in that size range, and we never see them because they just whiz on by and they're so far away that there's not enough reflected light for us to see with our naked eye. We can spot it with a telescope, but we can't see it with the naked eye. So if there is a moon, a kilometer in diameter, 300,000 miles away from Jupiter, you're not going to be able to see it because there's just not enough light being reflected by it.
Well, I know what you would be doing on
Jupiter.
You'd be calculating orbital elements of new moons.
But the bigger moons, definitely you'd be able to see, but they change position hour by hour. There's one of the moons, Io. It's a modest sized moon. It's smaller than our moon, but it's still a pretty good sized moon. and it takes only 2 days to orbit around Jupiter. So if you did have a solid surface that you could stand on, you'd look up in the sky and you would actually be able to see Jupiter moving across the sky, just standing there, or not Jupiter, see Io moving across the sky just as you're standing there watching it. That's how fast it's moving. All right.
Yep. I'm just seeing if there was another follow-up question on this. No, it looks like it's a comment. Margot mentioned that we had heard that each of these two gas giants had huge numbers of moons moving at different speeds, and thought that they would look incredible if you could see them. They would.
Yeah,
it probably would be incredible.
Yeah, I was watching a series on Netflix. It's called Away, which is actually a pretty good series, but it's now about the first human mission to Mars. And the entire series is not about the actual what they do on Mars. It's all about their trip to Mars and all the problems they have on their way to Mars. And in the last chapter, they actually land on Mars and they're looking around and they've got a scene where it's broad daylight and they look up and they see both of Mars moons. And I sat there and said, no, because they look really big. and Mars's moons are very small. So, but
they have to take
dramatic
liberties. Yeah,
right.
dramatic license. Yeah, it is Hollywood. All right.
Somebody asked me the other day what movie. In fact, John, it was when John and I were doing the program for some donors, and one of the kids asked what movie most accurately depicts space flight.
Right.
And we finally decided the only one that fairly accurately depicts space flight was the Apollo 13 movie.
Yeah, that's true. Yes, it's almost a documentary.
Right.
Yeah. So, if you're done with your
yeah, I'm done with M5. Other than I was going to mention that the M for M5 stands for Messier 5. It's part of the Messier catalog from Charles Messier. Charles Messier was an astronomer in France who lived in the 1700s and cataloged all kinds of interesting objects. But it was actually discovered closer to the turn of the century, in the early 1700s, 1702, by a German astronomer named Gottfried Kirch. And it was incorporated into Messier's catalog. Not all of the Messier objects were discovered by Messier. In fact, some of the Messier objects are fairly recent, but were added to the Messier catalog just out of consideration to his efforts.
And Messier, he knew of several of these objects from other people who had seen them before him. He was the first one to actually make a systematic catalog of them, so he didn't discover them, he just cataloged them. Speaking of Messier objects, I thought it might be interesting. I've got a few images of some of the other things we would have been looking at tonight had it not been foggy. So maybe we can share some of those if that's all right.
Yeah.
All right. So you just showed a globular star cluster called M5. Another one that we would have looked at later on tonight is M13. This is M13. It's one of the most popular globular star clusters in the night sky. And this is an image taken by Conrad Jung from Chabot. And M13 is 25,000 light years away. It's got at least 500,000 stars in it. And
it's very bright. It's very easily seen.
Yeah, if you are in a really dark sky location and you know right where to look, you can actually see it with your naked eye. It's easy to spot with binoculars or a small telescope. It's one of the most popular globular star clusters to look at by amateur astronomers because it's so easy to find and it's nice and bright and everything. So that's just one of the things we would have looked at. Another globular that we would have looked at is M3, and this is a Hubble Space Telescope image of M3. Hubble is able to resolve things much more finely than we can with our telescope at Chabot. So, this doesn't look quite so blotchy, but you see a lot more stars in it. And M3 is also about 25, actually, no, M3 is about 33,000 light years away. Another object that we would have looked at tonight is the Beehive cluster. M44. Beehive cluster is in the constellation Cancer, and it is what's called an open cluster. So M3, M5, M13, those were all globular star clusters, but the other type of cluster is called an open cluster. Open clusters are stars that all formed at roughly the same time out of the same cloud of gas and dust, which is how stars normally form. They form in clusters within a condensing cloud of gas and dust. As the cloud condenses, it becomes clumpy within it, and those clumps eventually further condense to form individual stars. Once the stars have fully formed, they've turned on, they start blowing the gas away, and eventually all the gas is dissipated, and that leaves behind a group of a couple of hundred to sometimes over 1,000 stars, all of which are more or less moving together through space. There are some gravitational forces that over long periods of time will eventually cause them to drift apart from each other. And again, these stars, since they all formed at roughly the same time and out of the same cloud of gas and dust, they have the same composition, they're the same age, and they're roughly the same distance from us. And because of that, any intrinsic properties that we see within the cluster, like you notice some stars are bluish white and some are yellowish or orange, those are true properties of those stars. It's not caused by, say there's a cloud between us and the star, so it makes it look orange. It really is an orange star. And the color of stars tells us the temperature of those stars. So we know that this is a hot star and this is a cool star. And this is how astronomers learn a lot about the evolution of stars as they go along, because the properties that we see are strictly a function of the mass. It's not a function of different composition because all the stars formed out of the same cloud of gas and dust. It's not a function of distance because they're all roughly the same distance away. And it's not a function of their age because they're all about the same age. So open star clusters like these are really interesting for astronomers.
Before you leave that,
Oops, sorry.
One thing that isn't an intrinsic property of those stars are the spikes that you see coming out of them. And I get that question very frequently because we see a lot of really beautiful images out there that have spikes, and we also see images that don't. And what you're seeing when you see a photo of stars that have either 4 or 6 spikes coming out of them is a diffraction pattern caused by equipment in the telescope itself. So some telescopes, like a reflecting telescope, will have a secondary mirror inside that's held in the center of the tube by something called a spider. And that spider basically has 4 vanes that attaches to the outside of the tube, or rather to the inside of the tube with a screw going through from the outside. And the vanes of that secondary holder diffracts light in such a way that you get these very attractive spikes. If you use a refracting telescope, which is one that just has lenses, it doesn't have any mirrors or bits of equipment in the center of the tube being held on with vanes. So you get perfectly round stars and without any of the distraction of diffraction spikes. But, it's all a matter of preference. When artistically done, they're really quite beautiful. And this is a great example of diffraction spikes.
Yeah. Yeah. Okay, moving along here. Another object we would have looked at tonight was M51, the galaxy, spiral galaxy that's actually feeding off of another galaxy. This is a black and white image taken with Nellie using a special camera that is a little more sensitive than your typical digital SLR camera. But it does not shoot in color. It shoots what we call monochrome, black and white. That allows it to see a lot more detail. And if we want to make a color image, what we have to do is put filters on that camera and shoot some images through a blue filter, then some through a red filter, and some through a green filter, and then combine those along with some of these without any filter, and that produces the final image. It's a color image. But this is, here we were just shooting with no filter at all, so we just get the black and white image. But you can see a lot of detail in here. You can see all the dust lanes. You can see the spiral arms, and this is a pretty spectacular image to look, or galaxy to look at through a telescope.
It also gives you a great sense of what kind of image scale we deal with our 36-inch telescope, because for those of you who have telescopes at home and have looked at this particular pair of galaxies, you're very easily able to see the entire thing. This isn't cut off because Gerald got lazy and decided to crop it. It's cut off because it's cut off. Yeah. And when we're looking through Nellie, we have to decide what part of M51 we want to look at.
Yep. Okay, let's see. This is M64. Oh, yeah. M64 is sometimes called the black eye galaxy. And again, this was a monochrome image taken with that same camera. And you can see this dense cloud of gas and dust here. In fact, there's an image taken by Conrad Jung of the same thing on Nellie, and he did it with a color camera. And then this is a Hubble Space Telescope image of just that central part. So if we go back to this, you see this dark region right here. The Hubble Space Telescope kind of zoomed in on it. And you see it's a lot of clouds of gas and dust there. And one of the things we've discovered is that the inner part of the galaxy rotates in the opposite direction as the outer part, and that's pretty unusual. That is weird.
That's weird.
That's very strange.
And it's also, you can also see that that's a very dense star forming region there.
Right.
Those are what are called H alpha clouds, and those red blobs are where new stars are being formed, which I guess isn't that surprising. The dark areas are usually molecular clouds containing a lot of available hydrogen gas to create new stars from. And there they are.
Yeah. So anyway, those are just some of the things we would have looked at tonight if it wasn't foggy at Chabot.
Yeah.
So let's try to catch up a little bit on some of the questions, because I don't want to get too far behind here. Lydia asked, and this is a question I don't think I understand. So maybe she can rephrase it, or he can rephrase it. In the star cluster, and I think we were talking about M5 at the time, but the globular clusters, how many years will it take for us to determine when one of the stars are dead from the true time of the star's death? I just don't understand.
Well,
that question.
I guess you can
elaborate.
You could start answering a question like that by realizing that the cluster itself is 30,000+ light years away. So any information that we're getting from that cluster, visual information, or any information for that matter, is 30,000 years old or 35,000 years old, right? So if we happen to see a star go nova, let's say, in the M5 globular cluster, we'll see that happen today, let's say, but it really happened 35,000 years ago. Right. So it's, we just have to realize that any change we would ever see in an object like that is something that happened long in the past. I don't think we will, likely see anything as dramatic as a nova or a supernova in a globular cluster in our lifetimes. It's probably not that frequent an event. It would be pretty interesting if we did see one. But Gerald, has there ever been a recorded observation of a nova or supernova associated with a globular cluster that you know of?
Not that I know of. Again, most of the stars in a globular star cluster are low mass stars, which are not going to go off as a supernova. So, all of the high mass stars have since gone away, with the exception of the blue stragglers. But I doubt if the blue stragglers have enough mass to go supernova either. So, we're probably not going to see anything like that. But
unless, of course, there was a collision that occurred just at the right time for us to see it,
right?
And that caused a supernova,
right? But you're right. When you look out into space, regardless of where you look, whether it's to distant galaxies or globular star clusters or nearby stars or even the moon, you're always looking backward in time. When we talk about how something is, 33,000 light years away, that means that light takes 33,000 years to reach us. So, a while ago, I showed you the Beehive cluster, which was that open cluster that I showed you. That's 577 light years away. So we see it the way it looked 577 years ago. So if something happens today, we're going to have to wait 577 years before we actually see it happening. So that can be confusing to people.
And you mean today in local Beehive time?
Yes.
Right. So not today in Earth time.
Yeah. And don't get me started about relativistic time and time dilation and all of that stuff.
Well, it makes it that much more amazing to think that we see supernova in other galaxies. We'll be looking at galaxies that are 25 million light years away and see some event take place. And now we're getting into some serious time travel. When you're looking back that far.
Yeah.
Speaking of that,
I'm sorry. Statistically, a star supernovas in a galaxy about once every 100 years. So, if you look at any one galaxy, you may have to wait a long time before you see a supernova in that galaxy. But, there are billions of galaxies out there. So we're discovering new supernovae quite often, several times a year. And it's because we're looking at all these different galaxies and one will go off here and it'll be another 100 years before you see one in that one. But next week, one goes off over here. So, we see a lot of supernovae very far away in other galaxies.
We're overdue.
We are.
Yeah, we are.
We are.
I want to point out Margot's question that Gerald and I were just talking about this before we started the program tonight, where Margot said, we heard that some plutonium from stars had recently been found in the floor of the Pacific Ocean.
Yep.
Why don't you talk about that? You actually read the article.
Yes, I've read it through once, and I should just to give you a sense of what we're talking about. A little over a week ago, actually right around a week ago, a paper came out by a team of astronomers who studied trying to figure out whether heavier elements came from supernovae or whether they came from neutron star mergers. And one of the things they came across was a lot of data that showed that heavy elements, elements around where uranium and plutonium are on the periodic table, there's a lot of them in the crust of the earth, especially down deep in the ocean where the crust has been kind of preserved. And when they started looking at, how these elements were formed, especially certain isotopes, they had to have formed in supernovae explosions, but they have half-lives, and the half-lives are not very long. So what that tells them is that if we can find that material here in the ocean, and it has a half-life, say, of only 30 million years, then that tells us that a supernova had to have occurred relatively close to the Earth sometime in that time frame for us to still find this stuff in the ocean or in the crust of the Earth. So I'm not sure if I'm explaining that very well, but certain heavy elements, isotopes of certain heavy elements, form only in either a supernova explosion or in the catastrophic merger of two neutron stars. Those isotopes don't stick around forever. They eventually undergo radioactive decay and become something else. And when we talk about half-lives, we're talking about how long it takes for, if you started out with 1 kilogram of that material, how long does it take to become a half a kilogram? And then how long does that half a kilogram take to become a quarter, and so on. So that's what we mean by half-life. And so the fact that we find some of these isotopes in such great abundance in the Earth's crust and at the bottom of the ocean floor means that there had to have been a relatively recent event within, say, 10 million years, 20 million years, 30 million years. There had to have been a supernova and or a neutron star merger close enough to the Earth to cause this material to rain down on the Earth and be deposited in the oceans and in the crust of the Earth. So that's what the article is about. Is a highly technical article. I was telling Richard earlier today, I went through it once, probably understood about 20% of what I was reading. So I'm going to have to go through much more slowly again to kind of really get down to the nitty gritty of understanding it. But it is very, very complicated. Lots of math in the article. So I don't want to bore you with all that stuff. But that's the general idea is the fact that this stuff is in the ocean and in the crust means that there had to have been a supernova explosion and or a neutron star merger within recent time, geologically speaking. The Earth is 4.5 billion years old. So to say that something happened 9 million years ago, that's very recent in time. So anyway, that's the gist of it. Okay.
No, it's a pretty good explanation.
Yeah.
It makes you wonder where this event was, though, because
Yeah.
we don't have any obvious supernova remnants very close to the Earth. So it means that maybe some of these elements are actually traveling through deep space from something that we aren't clearly able to identify. That anyway.
Well, yeah, and
it's a mystery.
Right.
We've shown images of things like the Crab Nebula M1,
Yeah.
which is the remnant of a supernova, and you can see that there's all this stuff that's just been blown off of the star, and it's spreading out in space. And if another star is maybe just a few light years away, a lot of that material is going to eventually land on any planets that are orbiting that star.
Yeah, and I guess that would be a potential source, because what the Crab Nebula is, it's less than 10,000 light years away.
Yeah.
So,
Well,
you
I'm
know,
not sure it would have come from that.
it wouldn't have come from that, but there might be other ones that were less dramatic
Right.
that left materials.
And the other thing you got to keep in mind is the sun is orbiting around the galaxy. It takes
Right.
230 million years to orbit around the galaxy. So a supernova that happened, say, 10 million years ago, we would have moved
Right.
quite a distance in that time. So
we could be sweeping it up.
right.
Yeah.
All right. Gotcha. Good.
Okay. Colvin 1, who is currently doing his taxes. I guess today's the last
yeah.
day for
Oh, that's
taxes.
right.
He better get
Yeah.
that done.
That's what I was doing all week.
But he says, what prevents them from combining? Unfortunately, I don't know when he posted that. So
I
I'm
think
not
he's
sure
talking-
what
he's
we were
probably-
talking about.
I think he's probably talking about stars in the cluster. We were talking about
colliding.
We were talking about gravitationally bound star clusters. What keeps them from colliding
It says
is
combining.
or combining.
So,
Would be the answer is mostly that there's a great deal of space in between those stars, regardless of how close they seem to us from a distance. So these collisions and combinations don't happen very frequently. That all
But they
being
can
said,
happen.
they
Yeah.
can happen.
Yeah.
And that being said, there are some globular clusters where we believe there are black holes in the center. And
Good. That answers the next
yeah.
question.
and it could be that those black holes were intrinsically formed in the globular cluster, and by stars combining and creating a scenario where there's enough mass to form a black hole. Or you go back to that other theory about the formation of globular clusters and say, well, it's the old core of a galaxy that had a black hole already. Less likely, but that's one of the arguments.
Yeah.
But probably it's due to just the fact that at the center of these globular clusters, there is enough gravitational attraction to create a combination.
And the black hole, and it's believed that a lot of them do have black holes at the center.
Yeah, later on in the summer, we'll look at a globular star cluster called M15, and we are about 95% certain that there is an intermediate mass black hole, a black hole consisting of several hundred solar masses in the center of M15.
Mario asks, can we detect the gravitational waves of a supernova? Well, I guess we have the ability to now.
LIGO does, yeah.
Right.
Yeah, LIGO has.
A supernova gravitational waves are not very strong, but a neutron star merger will produce some pretty strong gravitational waves, and they've actually now detected several of those.
I'm going to see if I can pull up a picture of LIGO. Because probably a bunch of people have no idea what we're talking about.
Yeah, LIGO is a device, a system. Actually, there's a couple of different ones that are designed to detect gravitational waves by having two very, very long tunnels at right angles to each other. And they shoot a laser beam down the tunnel. And if there is a gravitational wave that passes through us, it will deflect the laser beam a very slight amount. And by measuring that, they can determine whether or not there's a gravitational wave that has passed by. And they have to use more than one to make sure that they aren't being fooled by some localized event that temporarily deflected the laser, like an earthquake or something like that.
Let me see if it's hard to find a decent photograph of it because they have to be aerial photographs. So here's a picture. It'll give you an idea of what LIGO looks like. And here it is. You guys see that?
Yeah, there you go.
Yeah.
All right.
Very good.
So you can see how there are two arms of the instrument right angled to one another, all the way out here like this, all the way out here like this. Oh, usually surrounded by desert or farmland. There's I think 3 of these now. Is that right?
Yeah, I think so.
I think it's
there's at
3 or
least
4. Yeah.
there's at least 2, and I think there's 3 or more.
Yeah.
Um,
And then the instrumentation is in the building at the center. And when we say that we are able to use this to detect neutron star collisions, we were able to figure out roughly what part of a swath of sky that collision took place in. It's like we know that it's in some like 30-degree angle, and it's not a pinpoint
Right.
detection like we would have with a telescope or a radio telescope. But it's not bad. It's a whole different way of researching the cosmos using gravity waves. Who would have thought?
Einstein would have thought.
Yeah, I
Einstein would have
guess.
thought. Yeah.
Rob asks, when things go back to quote normal, will you guys be doing these virtual viewings? And yes, we are still going to keep doing them.
Another topic
after we
we
go
were
back to
talking
normal.
about before
Yeah.
the program
Yeah,
tonight.
yeah. Right now, the plan is for us to keep doing this, but it's going to depend a lot on you folks because as long as we have an audience, we'll keep doing it. But if we start losing the audience because people can come back up to Chabot and actually look through real telescopes, then that may change. But right now, the plan is to continue doing virtual telescope programming after Chabot Space and Science Center reopens.
Yeah, it may not be as frequent, or it will be on a different night. We'll figure something out.
Here's a good one from Larry. Why don't the cluster stars, I think he's talking about the globular clusters, disperse into the galaxy? And the answer to that is my favorite answer for most astronomy questions: gravity.
Gravity. Yeah.
There's enough mass in the clusters to keep them together.
Remember, those stars are in orbit around the clusters.
Yeah. They also are out in the, like Gerald said, the halo of the galaxy, so they don't interact with other stars in the galaxy enough to get them to get dispersed.
Yeah. And more importantly, they don't interact with all the gas and dust that's in the main disk of the galaxy, which means there's no gas and dust to form new stars. So that's why all the stars in the globular star clusters are so old.
Yeah, and the effect of gravity falls off pretty dramatically with distance. But that all being said, you've got all of the stars in the globular cluster attracted to one another, in orbit around one another, and you have the cluster itself in orbit around the center of the Milky Way, and the Milky Way is in orbit around a gravitational center consisting of our local galactic cluster. And but even though those galactic forces are, or rather those gravitational forces are much weaker, there is enough of it to keep things bound at that scale. But the globular cluster's strongest gravitational force is from itself. And so the stars remain held together.
Yep. Okay. Any other questions? Let's see. Are you looking just at Facebook, or are you looking at YouTube?
I'm looking
also?
at both, but there's a lot of comments as well as questions here. So
well, I got something I was going to show people. Why don't I open up this other view here? Here we go. So we've been doing a fair amount of programming at Chabot about light pollution, and not only on the effects of light pollution on astronomy and amateur astronomy, but on wildlife and other aspects of human existence at night. And we've been looking at all of the different human contributions to light pollution. And one topic that comes up is the Starlink satellite system. And I don't have a, I don't have a really strong opinion one way or the other. And I'm not going to say anything to insult Elon Musk because I don't want him coming after me.
Right.
But I mean, look, the
Coward.
Starlink, look, yeah, I am. I'm a coward.
He'll
The
put you in
Starlink,
orbit around Mars or
that's
something.
right. He'll send me to Mars. I don't want to go to Mars. It's a nasty place. The Starlink system is meant to address a real problem. It's meant to address the fact that half of the people in the world are not connected to the internet, and a low orbital satellite system might be one answer to that problem. If you accept that it's a problem in the first place, there's others I know who would say, yeah, those are the lucky people.
Right.
And it all depends on your interpretation of being connected in the first place. But it definitely has a visible impact on amateur astronomy and astrophotography and professional astronomy as well. Yeah, and so I want to show a picture of what we're talking about. So this is a picture of
Wow.
a recent comet, and I don't know which comet this is. I think it's the one, I'm looking at the ion tail, and it looks very familiar. It looks like it was the one from
Was
a
it
year and a
Atlas?
half ago. Yeah, no, what was the one that
What
was
does
so
it say down in
bright?
the corner?
It has the photographer's name, Daniel
Oh.
Lopez. So I don't know the name of the comet. It doesn't really matter. What does matter are all of these lines that you see. So this is a series of exposures, probably a half a dozen to a dozen 30-second exposures of this comet. And all of these lines are caused by Starlink satellites. And these satellites are small, but they travel in clusters. And there are plans to have as many as 42,000 of them in the next 10 years orbiting the Earth. And these are low orbit satellites. They tend to be anywhere from 200 to 300 miles above the surface of the Earth. They last for anywhere from 5 to 7 years before they turn into fireballs and have to be replaced. But you can see how, from the news, how SpaceX has basically created a Starlink factory where these things are flown frequently into space. They will be able to replenish them, but they cause a significant amount of light pollution in our photographs. And what I wanted to show you is how the amateurs are able to deal with this. So this is a single frame of, you can see a galaxy here, and it's a single frame, probably it's a 5-minute shot. And here are the Starlink satellites causing streaks as they travel through the field of view of the camera. But when you start stacking the photos, like I've mentioned that earlier for our M5 photos, we were stacking the photos. The stacking software is able to detect from one frame to the next whether something belongs in the image or should be rejected from the image. And the software is smart enough to clean up the image and get rid of those streaks. Here's 10 frames, here's 50 frames, and you can see that, hey, this is a perfectly decent astrophoto. And even though there were satellites traveling through the field, there's no evidence of it in the final result. However, from the perspective of professional astronomers, these are all of the rejected pixels. The lower right corner is all the data that was thrown away by the software. And this is data, right? This might be containing the information that a professional astronomer is interested in looking at. Amateur astronomers, we just want to create nice pictures of these cool objects. Professional astronomers may be detecting something that is just barely detectable, and that kind of data is going to get polluted by the Starlink trails and by whatever else. I mean, there's going to be a dozen companies doing the same thing over the next decade or two. So it's a real problem, but at least it got their attention. One of the things SpaceX has done is you can see here's an image with a streak going through it. That's a single Starlink satellite. What they have done is come up with black coatings for the satellites that lower their reflectivity. And you can see that the next frame over on the right is one that has what's called the dark sat coating on it. And it cuts the amount of reflected light by 50%. It's a nice effort. You know, they didn't have to do that. Nobody's telling them to do that. And I'm glad they're at least thinking about it. We got their attention. So we'll see how this all plays out. I guess our imaging software is certainly going to get better and better to deal with it, but we are concerned about the professional astronomy efforts.
Yeah, and
you guys have any thoughts on this?
Yeah, one of the things to point out, that image that you showed where there's the spacecraft has this dark coating on it, so it doesn't reflect light, so you don't see a streak through the image. But that satellite still passed through the image, and it still blocked a portion of the image as it during the exposure.
Yeah, and that could have been what they were trying to study. They lost data there. That's
right. Lost data no matter what.
Yeah.
Good point. All right. Well, that was my rant or story about Starlink. I'm trying to be kind about it. I mean, I have several friends who are astronomers who are going to be early adopters of Starlink because they get such lousy internet service from where they live. It's like, okay, you can't beat them, join them.
My son lives up in El Dorado, and he's going to sign up with Starlink.
Yeah.
Yep.
All right.
So, where was it? That question, I missed it again. Oh, there it is. Stephen asks, could the old Voyager space probes still send an image from interstellar space to Earth?
No.
No. Well, they couldn't they? There's just nothing to take images of.
Yeah, I don't believe they can transmit imagery anymore.
Not enough power left.
Yeah, I think what they're doing now is basically just sending radio signals, and those signals are pretty weak.
They're weak, but they're able to learn something from the weak signals coming in because those signals are interacting with magnetic field phenomena in the outer solar system.
Do they still have teams that are actually actively listening to the Voyagers?
I'm not sure if I'd call it actively. There are still people who are periodically looking at data. They continuously are recording data from it, but they're not. There's not somebody sitting at a desk 24/7
with a really long beard. Waiting for the next signal from Voyager. Somebody was asking, something seems different. We could see all three of us so clear tonight. Well, that's because we're not at the observatory tonight, and we're having a virtual program. So we have good artificial lighting tonight. So that's why you're able to see us so well.
Yeah. The Chabot Space and Science Center right now is in the middle of the Oakland Nebula.
Yeah, that's right. All right. Any more questions from folks? Because if not, we're at 10:30, and we managed to deliver an hour's worth of material. Anyone else? Anything on YouTube, John?
No, just comments. I think I got all the questions.
Well, while
If
you're
not, we'll
commenting,
get you next time.
yeah, while you're commenting, we want to remind you that the Chabot Space and Science Center is still closed. So we do not have the revenue that we would normally be getting from admissions. So because we are still working on exhibits and developing new programming, plus all the virtual programming that we're doing. We still need a source of revenue, so we're very much dependent on those donations. So if you want to take a minute, if you're on Facebook, click that donate button that you see in the comment section there. If not, you can go to Chabot's website. It's chabotspace.org, and you'll find a donate button at the top of the page there. So either way, if you would take a minute to help us out, we'd really appreciate it. Also, if you know of any corporations or philanthropists who are looking for a nonprofit organization to help out, think of us. All right.
All right. Thanks, everyone. You enjoy the rest of your weekend, and we'll see you next week.
Yeah, get those taxes done if you're still
Yeah,
working on them.
don't forget your taxes. That's right.
And happy
All right.
Astronomy Day.
All
All
right.
right, guys.
Yeah.
All right, guys. Take care.
We forgot to say Happy Mother's Day last week, but
Oh, God.
oh well.
Okay.
There you go.
Well,
Good night.